Hey everybody, and welcome to another episode of Space Science with Python. Today we are going to work with a numerical NEO model by Granvik et al. From the year 2018 from a paper, and the paper title is quite obvious. It is called the Debiased Orbit and Absolute Magnitude Distributions for Near-Earth Objects. So what they do in this very large paper is they generate a numerical or an artificial NEO model with different sizes or absolute magnitudes and also with different orbital elements. So what they try to is they try to create a model that is unbiased by the observations we do with our telescopes to provide a really like a potential true distribution of NEOs in our solar system. Of course, they can't do it for all sizes and so on, so they limit it until I think, 25 meg or so, or 24, but this is quite sufficient for our purpose. And how they do it, well, they integrate or they do some long-term integration from different potential source regions. This is quite a difficult task to do, of course. I mean, also to make it in an unbiased way, but they put a lot of thoughts into this and into this large paper. So if you want to go into the details, I would suggest to read through the paper to also get an understanding of the biases they try to get rid of the resulting orbital distributions and so on. So we are not going to analyze this model, but we are going to really use the model for our purpose. Fortunately, at the very bottom of the page, they provide also the link to the data of this NEO model here, the number 3. And we are going to use this model to create our artificial NEO model for our telescope observation understanding. And for this, I would suggest we move to our new Jupyter notebooks, the Jupyter notebook number 12. As always, it is in the GitHub repository, so of course you can download it for free and take a look into the script and also do your own computations. And before we start, what are we going to do today? So today we will download the model, we will take a look into the model and how it looks like, and then we will also put some thoughts into how we can even larger model that allows us later to get some kind of normalized distribution or detection distribution that we can use in our sky maps. So as I showed you in the one of the last sessions, we created some sky maps to see where the NEOs are visible. But now with the NEO model, I would like to create some kind of detectability map, like a probability density function, but a little bit more in a more sophisticated way. So I want to have a normalized sky map, so not with actual dots, but really with densities, because these are artificial NEOs. And of course, we really can't be sure if these objects are really there. It's more like as I said, you can consider it as a probability density function. And to do this, we need to increase our model a little bit. I will explain you soon what I mean by that. And then afterwards, and this is then the part of another video, we take all this new huge model and all the compute the apparent magnitude, and then use kernel density estimators, but in 2 dimensions and considering also spherical coordinates to create these unbiased normalized probability density function of the detectability of NEOs. So this is part 1. And next time, part 2, we will conclude then using this Granvik model. And then even this year, so we will conclude the entire project this year, we will use telescope properties to get even a way better understanding of how NEOs are detectable in the night sky. Now let's move into the script. The very first part of the script here in this first section or chapter is quite easy to understand. We import some libraries here in this part. We are then loading or setting some matplotlib styles and then also create a directory where we are storing our Granvik model. So you see here the Granvik model will be stored as a gzip file, and then later we need to unzip it. So let's first create this file here. And you see now that, not yet, but this will be our future path where we store our data. Now you see the raw data directory has been created. In cell number 4, we can now download our file. So this is also quite straightforward, and we just wait for a few seconds to download the file. The file has been downloaded, and we see now here in raw data our gzip file. So let's extend this a little bit, and there you see the gzip file. We use now the standard library gzip and also shuttle to unzip the file. This is being done here in cell number 5. And now you see our final .dat file that can be loaded in the next part in cell number 6. The content of the file is also explained in the README that is part of the repository. So I just copied the content here so you can take a look. We have the semi-major axis, the eccentricity, inclination, longitude of ascending node, argument of perihelion, the mean anomaly, and the absolute magnitude. So if we take a look at the model, we see here all the files, and you see we have in total 802,000 NEOs in this file. Now that's basically it, and you see we have here everything in degrees and also in AU, and for SPICE to understand the data we need also to convert it in kilometers and respectively also convert the degrees into radians. Now first in cell number 8 we load some kernel files for SPICE, and then in cell number 9 we are then converting the degrees to radians, and also we add the perihelion here based on the eccentricity and the semi-major axis. We also afterwards convert then the values in AU to kilometers, and this is basically it. So we enrich our data frame a little bit, and this takes a few seconds because, well, 800,000 rows is quite a lot. So this is now done in cell number 9. Now it becomes a little bit complex, because the question now is how do we create our normalized distribution? And this is another section here going on with cell number 10, and I put some text here for you to understand. But before we dive into it, let's take a look at a small orbit. We have a lot of orbits now that the file provides. So maybe an orbit that looks like this. Here's now written perigee and apogee, so it's an Earth-centric model, but it still counts for our Sun-centric system. Now imagine here is the Sun. We have here the NEO. We have a mean anomaly, which corresponds to an orbit. An object is somewhere here. We don't have the epoch, so well, the mean anomaly doesn't make any sense without an epoch. So we can set any artificial epoch, which is fine. And yeah, this is basically how our orbit looks like. But the point is now, for example, I mean, theoretically, this could happen if we have all mean anomalies with a certain value that corresponds to the aphelion, then all artificial NEOs are at their farthest point. Now, if we compute the corresponding apparent magnitude, this will lead to a huge bias, even in our unbiased model, because every NEO is very far away and we compute its faintest position. This could also be the other way around, if everybody would be here at the perihelion. So we have to somehow define a way where we have brightness values that are independent of the position. Now imagine the 800,000 orbits. What we do, we will populate the orbit with a lot of NEOs, and then later we compute the apparent magnitude of each NEO on each orbit, plot them on the sky map, and then normalize them by the number of appearances, so that we get a normalized and then corresponding probability density function of all these NEOs. And well, the point is, how do we do this? Well, I just wrote here in the markdown that we need something with equal angular distance. And what does it mean? Because if I put now here 10 NEOs with equal distance on this orbit, this wouldn't represent the actual, let's say, dwell time of the NEO on the orbit. Because here at the apogee and at the perigee, or along the entire orbit, the dwell time of the object is a little bit different. The speed of the orbit is also different based on Kepler's law. Because here at the apohelion, the object moves very, very slowly. So the time between a position here and here is maybe similar, let's say a few months, than here in the perigee. So for example, the movement from here to the lower part could be the same time as at the apogee for a very short distance. Now, this means that the dwell time of the object at the perihel is way, way smaller than at the apohelion. So, which means that the NEO that is now here in a let's say brighter state, this time, this appearance time in this let's say brighter state is way shorter than at its fainter state. So to make it more clear, the NEO moves very slowly here, so has a lot of time moving very far away from the sun. So here at the aphelion, it has a lot of it is, let's say, between here and there, it's like a few years, for example, and here at the perihelion only a few weeks or a few months, which means that we have, of course, to take into account that the NEO is fainter for a longer time than brighter. Yeah, I hope you can follow me a little bit, because it's maybe a little bit difficult to understand without an animation. Well, I hope you get what I want to say. So basically, we have to consider the different times, the dwell times of the NEO and its corresponding brightness in this region. So this is basically what we need to take into account. And the question is now, what kind of angular value does it represent? We have the mean anomaly, we have the eccentric anomaly, we have the true anomaly. So there are a lot of different values in there, and I would suggest that today we are comparing the true anomaly with the mean anomaly a little bit to get you an understanding how they differ a little bit. So here I have a small function that converts the true anomaly into a mean anomaly, and I do it this way round because SPICE only uses the mean anomaly, not the true anomaly. So this cell number 10 is simply a function. And now I would suggest that we create an artificial NEO. So something like this. We have a perihelion of 0.5 AU, we have an eccentricity of 0.7, and all angular values are 0, because let's take only a two-dimensional view. We only take the XY plane, and then some artificially set ephemeris time, cell number 11. Now in cell number 12, 13 and 14, we are computing now three different things. First, we are creating the orbit, and we do this by using the mean anomaly and compute the state vector in very small steps, 0.1 degrees, so that we have a very dense plot later on that shows us the orbit of the entire orbit of the NEO. We do this in the for loop here using SPICE function conics, and then we append the results in x and y coordinates, so only the first two results, convert them into AU and put them into a sample trajectory list. So this is what we do here in 12. Now we do the same thing in 10 degree steps for the mean anomaly, so with a very low resolution, and I said we use maybe 10 degrees for our simulation as well. And then in cell number 14, we use the true anomaly. So this is like the same thing as before. It's just a copy paste of each cell. First, we have a high resolution to plot the orbit, then low resolution for the mean anomaly, and the same low resolution for the true anomaly. And what we do now is we are plotting now our results. We do this in a two-dimension or in a two-grid plot. We put a plot at the top and one in the bottom. We do this with the function subplots. This is 2, 1, indicates that we have two plots along the y-axis, and along the x-axis only one. So we have one plot and below another plot, and they share the x-axis. So we set it with share x equals true. Now the upper plot and the lower plot, they will show us the orbit, and also then the mean and true anomaly respectively. So first we set the sun at the center at 0, 0, a yellow dot. Then we plot the sample trajectory as a dotted line, and then we add the mean anomaly in 10-degree steps with green triangles. And below we create the same plot, completely similar, but we set the true anomaly in 10-degree steps with orange axis. Yeah, so this is just for visualization purposes. And then we set some labels. So let's execute here cell number 15. And let's take a look here at the mean anomaly first. So this is our x-axis, this is our y-axis, had equal axis ratio. So yeah, we don't see the result, the values now here, they're below, but yeah, let's use our imagination. We have here the sun, and you see that for the position of the NEO here as green triangles in 10-degree steps, but in the mean anomaly domain. Yeah, so you see here in the perihelion, the dwell time is quite short. So you see it's getting quite fast. It's really fast. You really, almost see or experience the velocity of the NEO before it goes into the apohelion region, becomes slower and slower. And there we have way more dots. And this also corresponds to a position that is way fainter compared to the perihelion position. Now, if we do the same thing with the true anomaly, you see we have the other way around a little bit. Yeah, so we have here a lot of dots, a lot of NEOs close to the perihelion, and only a few ones at the aphelion. So this is like the picture the other way around. Yeah, so we have like a very inverse appearance of the mean anomaly and the true anomaly. So long story short, we take the mean anomaly to enrich our orbits. Yeah, so we will use the orbital elements of one row and create 36 positions in 10-degree steps. But these 10-degree steps, they are not somehow equal. Yeah, they will correspond to the dwell time of the NEO. So we will have only a few at the perihelion and way more at the aphelion. Yeah. So then when we populate each orbit, we will unbias a little bit their, I would say, dwell time or position time at this particular parts of the orbit. So how do we do this? Now here in the next cells, 16, starting with 16, we set an initial epoch. Then we are removing the mean anomaly column because it's simply some random value, and we replace it with an index, with a list varying from 0 to 360 degrees in 10-degree steps. So this is now a column that contains the list of mean anomalies. And then afterwards, in cell number 18, we need to populate now, or extend our model. So we have now a single row with a single NEO, but the single NEO has a mean anomaly column with a list that contains 36 mean anomaly values. So what we need to do is we need to explode the list so that this particular or this single row is extended into 36 rows, and the mean anomaly is not a list but a single mean anomaly value. And we do this with the pandas function, where is it, explode. So we use the data frame and then say we use, then we apply explode, and we want to explode the mean anomaly column. And then again, the mean anomaly column contains a list of mean anomalies. Yeah, so this is what we do. So this is what we, execute now in cell number 18, and then also 19, we can take a look at the resulting data frame. And the resulting data frame will be quite huge. So let's wait for a few seconds until the results pop up. And again, this is a huge list, so this may take a few seconds. Yeah, and we are back. I had to make a cut because it took some seconds to execute this cell number 18 and 19. And now we have our final model with now, I don't want to do things wrongly, almost 29 million NEOs. Yeah, so this is quite crazy. You see here now the first 5 rows. Semi-major axis is similar, eccentricity, inclination. We go to the very right and you will see the mean anomaly, how it increases from 0 to theoretically 350, and then it continues with another NEO orbit and its corresponding positions. The next steps, I also wrote it here. The next steps are the following. In our next video, we will use this huge list and compute the apparent magnitude of each NEO. And using the apparent magnitude and also the positional information, we will create a huge sky map with all the positions. And then you will have the possibility to filter the NEOs, for example, by orbital elements, by their brightness, by their sizes, and so on. And you won't get a sky map with a lot of dots, but you will get a sky map that will show you the probability density function. So not like a single dot or something, but you can get the information like, okay, the probability to detect an NEO at this particular part of the sky in a, let's say, 10 square degree field is 1.2 NEOs or something like that. So this is our end goal. We don't want to, we can't compute the actual positions of each NEO. We can determine the probability density function. So what are the regions in the night sky that are most likely to be, the regions where you have the highest probability to detect an NEO. And I think this is quite interesting. This will be also our then final product when we also will use the telescope properties into this. The major goal should be to create something highly interactive where you can change the exposure time, where you can change the telescope settings and so on and get results in real time. But you see, we have 29 million rows of data, and creating a real-time application with this is a little bit, it's kind of difficult to get it running on a normal computer. You can maybe do it in the cloud, maybe with Spark or something where it's more responsive. Here we will create something interactive where you can change the settings, but then you still have to press the run button to get your final results. I think this is fine at the very end. So there are 2 more videos to come where we will then conclude our project, and I hope you will then use maybe the tool to improve it a little bit, to maybe deploy it into the cloud, or if you have your own telescope, to determine where you should look at night to get as many NEOs as possible, or to detect as many NEOs as possible. I hope you learned something. I hope you enjoyed the video. And if you have any questions, again, as always, reach out to me here on YouTube, on Reddit, Twitter, or Mastodon. And I'm looking forward to your feedback. And I hope that you will also dive into this model and maybe do your own maybe data analysis and data analytics of this model and compare it, for example, with the paper to get a better understanding and feeling of the Granvik model. As always, stay curious and see you next time. Thanks for listening.